that means that this transition is inherently very narrow, so we can do very, very high resolution spectroscopy on that transition. This is a setup at Imperial. In fact, this trap here is identical to the one used at GSI. We had them built at the same time in our workshop. So although it's being used for a completely different purpose, it is actually identical to the GSI one. And what we have is we have laser cooling beam coming through the center and a laser cooling beam going into the board here. So we have two cooling beams so that we can cool all degrees of freedom. And then we collect the fluorescence coming out sideways, and so we monitor the fluorescence, and we can also image the ions. So this is a student working on the track, and this is just to illustrate some of the important aspects. So this is the magnet, and this is the whole trap assembly. The trap itself is here, and so we have to have a way of getting the trap into the center of the magnet, but we need to be able to work on this board here, which is all the optics. So we have a crane here, and we slide the thing along, and then we have to lift it up into the magnet. That's the trap, as I say. This is the breadboard with the optics on it, and then this is the optical fibers that bring in all the light and take it away to the photomultipliers. And this is critical because if you're moving this board around, you need not to have to readjust all the lasers each time you move it. So everything is connected to this by optical fibers. And the procedure that we use is essentially to prepare the ion in this state, and then to interact with the laser for a period, and then to interrogate with this laser again, this blue laser. And if we see fluorescence, that means that the ion is still down here. If it's up here, there's no fluorescence. So after each time we've probed the ion, we either see fluorescence, which means it didn't change state, or we see no fluorescence, which means it did change state. So what we see is a plot that shows us the probability of excitation from this ground state to this excited state as a function of laser frequency. But I want to talk about why we see sidebands rather than a continuous spectrum. So really, you shouldn't think of these as one state. You should think of it as a simple harmonic oscillator. We're talking first about the axial motion. So it's a quantum mechanical simple harmonic oscillator, so it has well-defined energy levels, and there's well-defined energy levels up here. And when we do spectroscopy, we're driving the ion between one of these levels and one of these levels. So there are discrete frequencies at which that can occur. So there's the ion sitting in one of these levels, and then you get the carrier transition, which is where the vibrational state doesn't change, and then you get, you get a blue sideband, which is higher energy when the excitation in the simple harmonic well goes up, and a red sideband when it goes down. If it's already in the ground state, then from here, there isn't a red sideband because there's no state for it to go to here. So when it's really cold, you expect the red sideband to disappear, and I'll show you that happening in a minute. So here's a spectrum on that transition, and this is about 2 megahertz wide, and what that shows is that the temperature is about of the order of 1 millikelvin, which is what we expect. So the determination of the temperature isn't particularly interesting, but it's the first time that the temperature has been determined in this way in a penny trap by doing this ultra-high resolution spectroscopy. And you can see that these sidebands are very, very narrow, very, very narrow. They have a width of about 1 kilohertz, and that's because our laser has a width of about 1 kilohertz. This is the spectrum in the radial direction. And this is interesting because it shows the cyclotron motion and the magnetron motion. The cyclotron motion is fast, so that gives rise to these widely spaced sidebands. The magnetron motion is a low frequency, So the sidebands for the magnetron motion are very close together, and that's why each of these peaks is broadened. That's due to the magnetron motion. And what this tells you straight away, actually let me zoom in on one of these. Well, what it tells you is that the width of this overall structure is due to the cyclotron motion, because you're seeing a number of cyclotron sidebands. But because you're seeing essentially something that's like the Doppler effect, you'll see the magnetron broadening around each of these sidebands is quite small, and that means that the temperature of the magnetron motion is much lower than the temperature of the cyclotron motion. So although everything is in equilibrium, the cyclotron motion is just a different temperature from the magnetron. And I'll show you in a minute that temperature is actually, well here, that temperature is actually very low. This is zooming in on one of those sidebands, one of these sidebands here, at a higher resolution, and the width of this trace is only 300 kilohertz, and if you turn that into a temperature, it comes out to be about 40 microkelvin. But the Doppler limit, the normal Doppler limit for magnesium is about 10 times that, or a bit more. So it turns out that this motion, this magnetron motion, when it's Doppler cooled, the temperature is much lower than the normal Doppler limit, and that's something which it's understood, but it's counterintuitive. It's not what you expect to see. So normally people can only get these sorts of temperatures in cold atoms, where the cooling mechanisms are much stronger. But this is the first direct measurement in the Penning trap. This is a more recent axial spectrum. This one has a temperature of less than 1 millikelvin. And so these are the sidebands. What I want to show you now is that we can do sideband cooling, and what that is, that instead of probing these different sidebands like we've got here, instead of just probing them, we actually drive the ion on one of those sidebands. And the reason we do that is that we can then walk it down this ladder of energy states so that we can prepare the ion in this ground state. So if it starts, say, here, we drive it on the red sideband, so that's the first one below the carrier frequency. So here it goes from n equals 1, 2, 3, and it goes here to n equals 2. So we excite it with not quite enough energy to stay in the same vibrational state. It drops one vibrational state. And then when it decays, so it goes up there, then when it decays, it's most likely to come back without changing that quantum number again. So what we've done is we've warped it from that state to that state. And then we can carry on doing that over and over again. And then it should end up in this state. And then we said earlier, when it's in that state, there is no red sideband because there's no state for it to go to. And here's the demonstration that happens. So this is just the central three, it's the central three peaks from this spectrum here, but after the sideband cooling. So you see there's a very strong carrier. This structure is well known. It's not, this looks like noise, but it's actually a proper structure. There's no red sideband, but there is still a blue sideband. So the ion must be in n equals 0 because it's in the ground state, because it can go to n equals 0 or n equals 1 in the excited state, but it can't go to n equals -1 because there is no state. So this again, this is the first sideband cooling in a Penning trap. And if you measure the height of that sideband, it shows that the ground state is occupied 97% of the time. So that has applications in quantum information, and so far it looks very encouraging because this is a very high figure, and what we've also been able to do is to look at the coherence in that transition and to look at the heating rate on that transition, and they both appear to be very good so far. Okay, so just finishing now. So GSI, the laser cooling experiments there, have got to the stage where we can prepare a dense cloud of cold ions ready for sympathetic cooling of highly charged ions, either from the EBIT or from eventually from high trap. So that's now, and then the next measurement phase that we'll have there, we will start to do some sympathetic cooling. And then at Imperial, we've got these sideband spectra for the first time. These have only been produced in the last few weeks, so we're still analysing them, and we're still trying to get the best conditions that we can out of them. And what we will do next is we'll do proper study of the decoherence rate and of the heating rate. And we think that that heating rate is going to come up to be very favourable compared to RF traps. And I'm also going to show you here, if I can just take one extra minute of your time. So this is now an image of ions in our trap rather than just looking at fluorescence. And this is 11 ions, and we can prepare them in different states. So they're we call this a Coulomb crystal because they're so cold that they're just sitting in fixed positions relative to each other. But what we can do is, by changing the parameters of the trap, we can change the configuration of this crystal. So here we're increasing the voltage on the trap, and you can see that the ions are squashed down into different shapes of crystal, and eventually there, you just see it quickly, it goes into a flat plane. So we turn the voltage up, squeezes it down, and then we release the voltage again, and it goes back up to the line. And this is also interesting because in an RF trap, you can't have the same level of control as this without having lots of micromotion, and there's no micromotion in the penny trap. What there is, unfortunately, is the ion cloud, or the crystal, is always rotating, and that's why you don't see dots here, you see lines. That's because the crystal is rotating, so when you look from the side, each ion is smeared into a line. So that's a pity, but that's something that we're stuck with. I want to show you one. I won't show you that. I want to show you. Sorry, I'm looking for a particular. I'm looking for a particular picture. No, never mind. I wanted to show you our biggest crystal, which had 174 ions in it. Okay, so we've been able to prepare those Coulomb crystals as well, and what we will do eventually is that we will combine these techniques so that we'll be looking at the sideband cooling of the crystal rather than just of one single ion. So now I have gone on too long, and thank you for your attention.
Very interesting talk. I think there might be some questions.
I have a silly question about the laser cooling. At GSI, you introduced magnesium, singly charged magnesium, and you use laser to cool the magnesium or
Yes.
the ions? Okay.
No, but it's singly charged magnesium. So you'll have two types of ions in the trap, but at the moment it's just one type of ion. It's just the magnesium. So it's singly charged magnesium, which is laser cooled. And then we will also introduce the highly charged ions into the same trap, trapped at the same time, and then they will interact, and that will sympathetically cool.
The highly charged ions?
Yes, that's right. That's right. But at the moment, as I said, we've also got the resisted cooling as a possibility. Now, the resisted cooling, you can cool any species with that. That doesn't depend on having a particular atomic structure, but the laser cooling requires you to have an atomic structure where there's a transition that you can hit with a laser. So the resisted cooling is there as well as an alternative to the laser cooling. And the resisted cooling you could do directly onto your highly charged ions. So you can just put them into the trap and cool them resistively. So that's why we're looking at the resisted cooling at the same time. Does that answer the question?
Yes.
what is the limit of resistive cooling?
It's whatever the temperature of your resistor is, really. So in this experiment, it's actually not a resistor, it's a resonant circuit, which has an effective resistance, which is very high, which gives you a strong cooling rate. And the circuit is attached to the helium reservoir for the superconducting magnet. So that's at 4 Kelvin. And so the resistive cooling can take you to 4 Kelvin in an ideal world. In practice, it may be a little bit higher than 4, but that's the limit it can go to. Whereas, obviously, the laser cooling can take you down further.
I think
So after that, you have to disconnect.
Sorry?
After that, you have to disconnect.
Yes, that's
Otherwise,
right.
it will heat.
That's right, yes.
I think we also have another disadvantage for resistive cooling. It's for the gravity mode only.
Yes.
For individual.
Yes, and that's an interesting question, because the resistive cooling talks mainly to the centre of mass mode, but there appear to be mechanisms that will couple the internal motion into the centre of mass mode. So if there are any imperfections in the electrodes,
Okay.
and also if you have any mixed species in the trap, so if you don't have one pure species but you have other charge states as well, then all the modes start to talk to the centre of mass mode, and therefore to the resistive cooling. So we've worried in the past about to what extent the whole cloud is cold when the centre of mass mode has gone away. But I think that you do cool all the degrees of freedom, but you rely on sort of second order processes to do that. So it's bound to be slower than the cooling of the centre of mass.
It must be. Do you know how big is this high order coefficient of this, like the magnetic field?
Oh, I think it's I think the main thing is. So I think the two main things are first of all imperfections in the electrodes. So you know that you can't make a pure quadratic potential.
No.
So if the ions are moving in a region where the potential is not perfectly quadratic, then everything is coupled. And certainly initially that's the case, because the ions are moving throughout this long region, and it's nowhere near harmonic over the whole region. So certainly initially it won't be the centre of mass motion only that's cooled, it will be everything. Okay. And then also the resistor is not connected between the two end caps, it's connected between the centre electrode and one end cap, and that means that it talks to other asymmetric modes as well as the centre of mass mode directly. And then if there are if there are impurities, then that means that the centre of mass mode is not the same as, the centre of mass is not the same as the centre of charge. And that also means that everything starts to talk to the external circuit. But it's something that we've worried about and argued about a lot, because it's a very important point. Because we really need, for laser spectroscopy, you really need the ions to be cold and not to have any motion, not just the centre of mass to be cold.
Sorry, I have another question about the second part of your laser spectroscopy. I mean, you have cooling lasers. After you cool down, then you switch off the cooling laser, looking at the fluorescence, or you just
yes. So with the sideband cooling, there are two steps. So you have a period of standard Doppler cooling, where you have all the lasers on. Then you turn those off, and you just drive that transition to the metastable state. Okay, so you do that with all the other lasers off. That prepares it in the ground state, and then the way you measure which state the ion is in is by turning on the cooling lasers again. But that, of course, that's a destructive measurement. So it tells you whether the ion was in the ground state or was in the metastable state, but it isn't anymore after that. So as soon as the cooling laser is on, it goes back up to the Doppler temperature. Okay, so as soon as you've measured it, you've changed the state that it's in. But so it has phases. It has a cooling phase, an excitation phase, and then a detection phase, and then you have to repeat the whole thing.
And that's in the visible light?
That's all visible. Yeah, that's all visible in our case. Well, it's nearly visible. So the cooling lasers are some of them are blue, 397 nanometers, just visible, and then the other one that we need is at 866, which is a little bit too far into the infrared to be visible, but it's close enough. And the lasers for that are easily available and well behaved.
Thanks.
Yeah, I have a question. I find you only have two directions in your laser cooling. One from
Yes.
down and the other from the side.
Yes.
And as I know, in the laser cooling of the neutron atoms,
Yes.
you usually have 6 directions.
Yes.
One down, up, sorry.
That's right.
So why? I mean,
Yes, that's interesting. It's because it's in a trap and it's oscillating and orbiting. In fact, you can use one laser beam. It's sufficient to use one laser beam because the ion. So, for instance, imagine I come in diagonally, then an oscillation this way has a component along the laser beam. So this motion is cooled, but this motion also is cooled because that also has a component of velocity along the beam. Okay? So in fact, one laser beam can cool all degrees of freedom, and it's because the ion its velocity is continually changing and it's oscillating. In the cold atom case, you need 6 beams when it's essentially a free particle, and so it can be moving in any direction, and therefore the only way to be sure that it will interact with one of the laser beams is to have 6 laser beams. But because then it will carry on. If it doesn't get cooled, it will just carry on moving in a straight line. In the trap, it will always oscillate, and then you can cool it when it's moving in the right direction. So it's easier than cold atom cooling because you have because it's oscillating in the trap. You only need one laser beam. Well, okay, you only need one. We use 2 because the construction of the trap makes it very difficult to have one coming in diagonally. And we used to just have a radial beam, which works fine, but it turns out that the laser cooling is much, much better when you have an axial beam as well. And I think that's because the radial motion is nearly decoupled from the axial motion. So even though you do get cooling of the other one, if you only cool one, the cooling is much stronger if you have a separate beam for the radial motion and one for the axial motion. And in the radial direction, because it's an orbit, you don't need to have 2 beams because it will always interact. It will always interact whichever direction it comes in from. Okay. Sorry, that's my hands don't have enough degrees of freedom.
And also this magnetron motion, you have to hit that.
Yeah, that's right. Well, I didn't talk about that, but yes, the magnetron motion is difficult because fundamentally it's unstable. It's difficult to cool, and so you have to position the laser beam at a different away from the center of the trap in order to make sure that magnetron motion is cooled. So that's an extra complication in this case.
Could you explain a little bit about the well-known effect according one of the temperature of one of the components to below the Doppler limit?
Yes, you mean that the magnetron is cold?
Oh, yeah.
Yes. Okay, I don't know where to start with that really. It's I think the best way to think about this is that the motion in the lab frame is complicated because you have electric fields and you have a magnetic field. And the way I like to think about it is to picture it not in the lab frame, but in a frame that is rotating at half the cyclotron frequency. And the reason for that is that in that frame, there's a Coriolis force which exactly cancels the force due to the magnetic field. So in that frame, the ion looks like it's just moving in an electric field alone, okay? And it's easier to picture what's happening there, okay? So in that frame, the potential, okay, the radial potential in the trap is negative. It's a hill rather than a valley.
You could use the blackboard.
Yes, I could. Okay. Okay. So in the laboratory frame, the potential does that. Okay. If you go into this rotating frame, it adds a term to this. It adds a term to this potential, which is also quadratic and depends on the magnetic field, and then it ends up being an effective potential that is also a normal harmonic potential. Okay, so in this rotating frame, there's no effective magnetic field, and there's a new effective potential, and the motion in that frame is just a straightforward two-dimensional simple harmonic oscillator. It's very, very simple. Okay, and in that frame, if you think about the laser cooling, you get something like the normal laser cooling limit for the motion. Okay, it's not quite the same, and that's because of the rotation, but you get something like the normal laser cooling limit. But then when you go back into the lab frame, okay, so in this, I'm now looking in the radial plane. In this frame here, you have motion in that direction, and you can have motion in that direction, so counterclockwise and clockwise. When you go into the lab frame, you go back into the lab, the whole thing is rotating, so this one becomes much faster, okay? And this one is going against the rotation, so this one becomes slower. And actually, it goes in the same direction still, but it's slow, okay? And so this is now the cyclotron motion, which is fast. This is the magnetron motion, which is slow. But they were equal frequency and just opposite directions. Here they're in the same direction, but one is fast and one is slow. And what has happened is that the velocity distribution for this, which was thermal at the Doppler limit, is spread out here, so it becomes hotter. But this one was thermal at the Doppler limit, and because the rotation goes in the opposite direction, it's been compressed. So when it comes into the lab, the velocity distribution is narrower than it was here. Okay, so here it was at the Doppler limit, or something like the Doppler limit, and here it's now much less than the Doppler limit. Okay, so it's to do with.
You really need to cool the one with higher than the Doppler limit, basically everything.
Yes, so this is the cyclotron motion, and the cyclotron motion, the prediction is that it's a factor of 2 or so higher than the Doppler limit. In fact, in our experiment, it comes out much higher than that. It comes out maybe 5 or 6 times the Doppler limit, and we don't know why. So that's something we're not quite sure about. So that appears to be significantly higher than what we expect, but this one is roughly where we expect it to be. So I don't know if that's helpful or not as a picture.
Okay, maybe one more. I think it's time to end the talk. Yeah. Okay.
Yes?
Will the Florence destroy the podium and arms?
Will the fluorescence destroy the cooling? So I don't quite know how you mean.
When you excite the atom, the ions to the high state.
Yes.
And this ions decay, it will emit fluorescence. I think this fluorescence will destroy the cooling state.
It will destroy the sideband cooling, yes. Is that what you mean? So when you prepare it in the ground state, so I'll use this again. So if you've got these things, if you prepare it in this state, then when you look at any fluorescence, it will come out of that state, and it could end up in any of these. Is that what you mean?
Yeah.
Yes. So yes, that's certainly true. With the Doppler cooling, it's in equilibrium. So you see fluorescence, but it keeps on. It stays in a thermal state at the Doppler temperature. But if you do the sideband cooling, as soon as you turn the fluorescence on, it goes back to the Doppler temperature, and therefore it's spread over lots of these states. Yes, so if once you've prepared it in this state, you mustn't turn on the cooling lasers. So you can manipulate the state, but you mustn't turn on the cooling lasers until you want to measure where it is. So that's what happens in all the quantum information protocols, is you prepare it, then you do all the manipulation, and then you turn your cooling lasers on at the end to find what state it's ended up in.
So the final picture of the iron crystals are actually at Doppler temperature.
Yes, yes, that's right.
Okay, I think everyone's satisfied. I think before we leave, I should give you we prepared more.
Thank you. Thank you. I open it.
Yeah. Okay.
Oh, thank you.
It's a pen trap. Not for trapping. For eye, called eye, the pen trap.